Hello, everybody. So this is our first video of the semester. This is the class for August 31st, 2021. Today, I want to start with recreating the histogram and the box plot. I did it towards the end of class. I want to make sure that we're all on the same page. I'm going to describe some statistical measures, numeric summary measures like mean, median, mode, percentiles, standard deviation, variance, range, interquartile range. Some of the more exotic ones, I will say that on my list here, the more common ones are in this first bullet point, and the less common ones as we move down the list. And then this is all really going to apply to quantitative continuous and quantitative discrete variables. And I will just spend just a tiny bit of time for categorical ordered and categorical unordered. Things in terms of graphing are a little bit easier, and preview things in terms of modeling categorical data are quite complicated. And in fact, there's a whole semester-long class on categorical data analysis. So plotting categorical data, relatively easy. Analyzing categorical data, quite hard. Okay, let me start with a histogram and a box plot. So a histogram, we take our quantitative variable, and I'll just say low values go here, high values go here. On the y-axis, we have relative frequency. And then we usually rely on our software to divide the variable into meaningful buckets, or at least buckets that are not sort of inoffensive. I mentioned in class that certainly feel free to change the default of how our continuous or discrete variable gets sort of binned. They're bins or buckets, you can think of them. But most modern software has pretty good defaults to where I personally don't mess around with it much. And so we then record how many of our levels, our unique levels, fall inside every bucket. So if I have 1, 2, 3, 4, 5, 6 buckets, I just record how many of my unique levels of our quantitative continuous or quantitative discrete variable fall in this first bucket, second bucket. Oh, this one's kind of popular, less popular, and then I might do something like this. And I specifically went with something that does not necessarily resemble a bell curve, although that I think is a lot more resembling a bell curve than what I drew in class. But if I sort of take this out a little bit more, and I sort of keep going, and the reason is because I want to give this thing a nice tail. So this is a distribution. Distribution tells us which values of our variable are more or less common, right? So more common values are here, where the relative frequency of observing, say, these values are high. The tails are along both sides of that distribution. And I specifically want to give this guy, for descriptive purposes, a nice long right-hand tail, where the values are really high, but quite uncommon relative to the sort of the bulk or the middle of that distribution. And so what I drew in class looked something like this. Okay, we have low values, bulk of the distribution, a nice long tail on the right-hand side, and then we have these two outlying values. So I'm going to call these what they are. These are outliers. Right-hand side tail, left-hand side tail, middle of the distribution. So if I now sort of make the box plot for these data, I'm thinking, all right, well, in my box plot, I need a minimum, a maximum, I need that defines sort of the outer bounds of the box plot. Then I need sort of a middle value or the median, and then sort of the percentiles, the first quartile or the 25th percentile, the third quartile or the 75th percentile, and then in a box plot, our outliers will be marked. So what I'm going to do is just go ahead and just mark these outliers. And then get my box. So maybe I'm thinking the middle value is somewhere right in there. And I'll make sure to formally define these. This is the median. And I want to make sure to formally define it because, again, I did it towards the end of class, and I want to make sure that you guys got that information down. At least it's on video, so you can go back to it. I specifically drew this to where there are 2 high outliers. There are no low outliers. So this is just going to start with the whisker part. And then we're going to go like that. And probably not this wide. And I'm just going to make it a little bit more pretty. All right, the middle just becomes a line that is marked. Right, this is the median, and that's just going to be the vertical line. If your box plot is horizontal, it will be the vertical line inside the box. If your box plot is vertical, it's going to be the horizontal line that's inside the box. It's the median, also known as the 50th percentile. Also known as Q2, or the second quartile. Quartile, quarters, it's the second quarter. The minimum is then going to be this point right here. Remember that this is just a bin. This is just the lowest bin. The minimum of the data is here. And that just translates down. This bin sort of aggregates all of these data points together into this bin. There's not that many. That's why that bar is quite low. The first quartile is going to be the one edge of the box. And this is also going to be the 25th percentile. All right. And then this edge of the box is going to be Q3, or the 75th. Whoops. Percentile. These are sometimes called whiskers in some software, particularly older software, maybe even older than SAS. You're going to see this called the box and whisker plot. These whiskers describe data that are away from the middle, but are not outliers. That's why I stopped this whisker here, which corresponds roughly to where this bin ends. The outliers are usually marked separately. Not always, but are usually marked separately. And then the maximum, of course, is this outlier right here. This is the maximum. Okay? 100% of the data lies right there between the minimum and the maximum. Because this is the 25th percentile, I'll use a different color now. Because the edge of this box is the 25th percentile, 25% of the data lie below it, right? So this is the bottom 25%. And then this is the median, or the 50th percentile, or Q2. So that means 50%. We can say bottom 50, top 50, that doesn't matter, right? Because there's the same amount of data is inside the top 50 as the bottom 50. %75% of the data is here. And then, of course, if I had a line for the maximum, then 100% of the data is going to be below the maximum. So you can see that together, these are really quite powerful graphical summaries where, well, first of all, the box plot, I made no secret that it's one of my favorite graphical summary tools. First of all, it's one of the few that specifically isolates the outliers. The histogram, you're going to have to visually assess whether it's an outlier. Here, I made it quite clear there are two outliers, but you know, if someone came up to me and says, well, actually, that's also an outlier. Well, it could look that way, but the box plot has an algorithm that specifically isolates the outliers. And this algorithm, again, you know, when we are teaching statistics in the 21st century, in 2021, we have to say most software, because to be honest, I have no idea what Tableau, for example, does, or quite frankly, Excel. But most software packages define these outliers as, I'll use a different color still. Our outliers usually by default, and of course you can change it in most software, is Q3 plus 1.5 times the interquartile range. And then we're just going to note that the interquartile range is the difference or the distance between the third and the first quartile. So the size of the box is the interquartile range. IQR, I won't write it out. It's the interquartile range, the distance between the third quartile and the first quartile. It is the middle 75% of the middle 50% of the data. So then I will adjust this to say the bottom 50, that is below the median. Interquartile range is the middle 50% of the data. Right, middle 50% of the data is covered by the box. Bottom 25 is below, top 25 is above. These outliers are defined as 1.5 times the interquartile range plus Q3, right? So it's at least 1.5 interquartile ranges above Q3, or 1.5 interquartile ranges below Q1, right? So in this example, there are no low outliers. If they were there, then these would have to be at least 1.5 interquartile ranges below Q1. And yeah, I'm pretty close here. I'm pretty close with my little drawing here. You know, it's fair to ask how 1.5 came to fruition. These are, again, reasonable defaults. Feel free to change them if your software allows. If not, don't worry about it. Okay. So really, I've talked about the median, minimum, maximum, interquartile range. Range, right? The range is just the maximum minus the minimum. And you should note that the range is not a particularly useful statistical tool to summarize data. That's because, you know, in most real data sets, you will have outliers. either on the low side or the high side or both. And so the range can be literally defined by outlying observations. Your typical results are going to be here in the middle. The range might be literally defined by atypical data. So it is not one that is used much in sort of statistical literature or for statistical purposes. It can be useful to identify data entry errors. It can be useful to identify sort of the absolute maximum range of possibilities. But for statistical purposes, I would definitely not recommend the range. Interquartile range is an underused statistical tool because I think it's really something that defines the middle 50%, the typical 50% of the data, whereas the median is the middle value, but it really doesn't have an interval there, right? The interquartile range defines the interval for the typical, the middle 50% of the data. And altogether, when we talk about Q1, Q2, Q3, even the minimum and the maximum, these are all together comprising percentiles. Percentiles are observations such that I'll say X% of the data are below. And I will even color code X% to match what I have here. And that makes it clear that Q1 is also the 25th percentile. The median is the 50th percentile. Q3 is the 75th percentile. The maximum is the 100th percentile. And the minimum is the 0th percentile. We've all had some experience with standardized testing. You always want to place in the 95th percentile for your standardized tests. Percentiles are important, for example, when we're studying birth weight and growth for children. There are very detailed percentile charts. All right, the mean or the average. In class last week, I never defined what the actual formula is. So the notation is X bar. We say X bar. And the formula, kind of long way, is 1 over n times first observation plus second observation, all the way until we get to the last observation. Just to make sure that we have our notation down. N is the sample size. X1 is the first observation. X sub n, this is the subscript, right? So X sub n is the last observation. And before you ask me, how do we know which is the first and which is the last observation, we can add things together in whatever order. So what X1 is, what X2 is. When we need to add things together is arbitrary. So we add up the values of our variable, we divide by how many we have, we get the sample mean, X bar. The median is, of course, just the middle value, but if our sample size is even, it does not correspond to a single observation. And if our sample size is even, then the median is the average of the middle 2 points. Then it does not correspond to an actual observed piece of information. So there's a couple of things to note about the average, sort of in this universe that I drew. There's a reason why I start with the percentiles, the medians, Q3, Q2, etc. The average, because of this addition that occurs, the average is usually quite affected by outliers. And that's due to the summation that occurs right there. The average is affected by outliers and, in general, extreme observations. Why do I say outliers and or extreme observations? When you say outliers, people can have very different ideas about what constitutes an outlier, but extreme observations, you know what? If most of my data, right, I'm looking at, okay, this is my 75th percentile right here. 75% of the data is below my arm. Then really, these right here are going to be kind of extreme observations, and they're going to affect this average. And what this means is that the average is going to be pulled towards the longer tail and often towards the outliers, especially in this case where we have outliers on just one side and not the other side. So it's affected and is pulled towards longer tail. It's pulled away from the center, which is really what we want the average to measure. We want the average to measure the typical value, the expected value, the normal value. And I'm specifically trying to avoid the word average value. We want the average to indicate a center of the data. But in the presence of these extreme observations and or outliers, it's going to be pulled away from the middle where the median lives. The median will always live in the middle, but the average will be pulled. So let me draw my average. So my average, my mean, might be here. Right? My median is going to be here. My mean is going to be here because of these extreme observations and the fact that the longer tail is on the right-hand side. And so, because of this summation, that mean gets pulled in the direction of the longer tail and or outliers. So if the entire picture were reversed, so the longer tail would be on this side, then the mean would be closer to those outlying observations. The mean that would be pulled to the left-hand side if the longer tail were on the left-hand side. And so the mean gets pulled away from the middle, whereas the median always lives in the middle, regardless of where the outliers are. So this makes the median most often the most appropriate measure of center. The average is only going to be around the median if our distribution is symmetric. So let me write that down. That's that special case that we sometimes talk about in mathematics. The mean is going to be approximately the same as the median only if our distribution is symmetric. When I say symmetric, I mean approximately equivalent tails. Approximately equal tails. So if you're entering a data set for the first time and you're not sure what the distribution of that data is going to look like, then the median might be your go-to default measure of center. But the average is nonetheless a very important measure as long as we understand its behavior relative to the longer tail and the outliers. Okay. The only one left, therefore, in this line is the mode. The mode of the data is the most common value. It's the tallest bar in the histogram. So in this case, the mode is right here. And the mode is not tied to outliers. It's not tied to where my tails are. It's not tied to whether my tails are approximately equal. The mode is simply tied to the tallest bar in my histogram. And it maybe has sort of a practical meaning, but maybe not a particularly statistically important meaning. Okay, let's move on. So we have now covered this line. All right. All of these are measures of center or measures of central tendency. What is happening in the middle of the distribution? Think of all of these things, summaries, even the graphical summaries, as tools to distill a large amount of data, and is usually large, or as large as you can get funding for. These are all tools to distill all of that information into a single number: the mean, the median, the mode, the Q1, Q3, the minimum and the maximum. You're still distilling information into a single number. And some of them are going to be more useful than others. All right. The next line, oh, I'm going to clear this off. The next line are measures of spread of the data or measures of variability. So the standard deviation, I will put the formula here. And formulas, by the way, similar to what I did with that formula up there, it's to indicate why the mean sometimes or very often is not the most optimal measure of center. Because we add the numbers up together, right, the extreme observation is going to blow up that sum. So similarly, pay attention to the formulas to understand how they work, not to memorize the formulas, right? Because the software is going to compute this for you anyway. So standard deviation. Sometimes it's SD. It was only invented in 1896 by Carl Pearson. So the standard deviation has been around for about 120 years only. Yet it's a very common measure of spread. In the sample, right, which so far we're just talking about your observed data, we're not talking about the population, we're talking about the sample. The sample standard deviation, the notation is X. It has a square root. And then it has a sum and a division. So let me write out the formula. And then I'll break it down for us. Okay. There's a little bit of shorthand in these formulas, and that's this summation. Right, this right here is a summation. So even the formula for the mean, I deliberately avoided the summation notation here just to get us going. But this sum, sometimes to sort of save space, we can write it in terms of a summation. So we can say this is 1 over n. Sum, this is a capital sigma for sum. I goes from 1 to n. I is this index on the bottom. And I goes from 1 to n, where we sum each observation. each ith observation is summed. So here, we're actually summing the difference between each observation and the sample mean, right? So this is the sample mean. This is the sample mean. We're summing, in fact, the squared differences between each observation and the sample mean. And we're dividing by n minus 1. So it's actually sort of a pretty complicated formula. Sum of squared differences between data and x bar, which is the sample mean, divided by n minus 1. So what I'm specifically trying to say is, okay, we sum things, divide by n. We sum things, divide by n minus 1. This is really an average, right? We're sort of taking an average here. And you think average distance that data lie away from the mean. This is the mean. Here's where it is in the formula. Here's each individual observation. And what you're doing is you're sort of saying, this is my average distance that data lie away from the mean. Okay, let's keep going with the formula a little bit. First of all, we have the square root sign. To get a real number, we have to make sure that we're taking the square root of positive numbers. So whatever we get underneath the square root has got to be a positive number. I suppose it can be 0, but that's a very weird case when all of your data are identical. And so your distances from each data point to the mean are 0. That is what we call a border, an edge case. So because you're summing squares here, right? You're summing squares, you're pretty much guaranteed to get positive numbers. When you divide by n, as long as n is greater than 1, if n is 1, you can't compute the standard deviation. If n is 2, you can. So you're summing positive numbers, and so the standard deviation, therefore, is going to be greater than 0. And we're not a math class. In theory, it can be 0 to greater than or equal to, but the case where the standard deviation is 0 is a really silly case. Maybe as a homework example, you guys can tell me the case where the standard deviation is 0. It's a pretty good homework question. Okay. Now, similar to the way the average works, where we add things up, we still have this adding things up inside the formula for the standard deviation. But worse than possibly extreme quantities, we're then going to go ahead and square it. So we're going to take the distance from every observation to the mean, and then we're going to square it. So when we are coming to the contributions of these outliers to this formula, we're going to take these differences, these two differences right here, between here and here, here and here, and square it, and then add it to the rest. So the standard deviation is 2 affected by outliers. So it's often inflated if there are outliers. It's inflated. But it's a very popular measure. In a lot of literature, you see the average and the standard deviation reported next to one another, where the standard deviation is like in parentheses usually. So it's not me saying don't ever use it. It's me saying understand where it might get things wrong. If there's a lot of outliers in the data, the standard deviation will look inflated. And what it really means is sort of an average distance that data lie away from the mean. We've already talked about the IQR, right? It's just the third quartile minus the first quartile. We already talked about the range. Notice that all of those are still measures of spread. It's how spread out our data are. We just finished talking about the standard deviation, so we're just left with the variance. So the variance, I think, is another one of those overused statistical summaries, because unlike the standard deviation, where it has sort of a logical, intuitive explanation, the variance really does not. So the variance is just the standard deviation squared. All right, so it's the sample variance. It's just S squared, right? Standard deviation squared. This too, if the standard deviation is affected by outliers, the variance is also affected by outliers. Again, doesn't make it not usable, but if you make your box plot, you see a ton of these guys somewhere, you know to look at the standard deviation, the variance, and the mean with a grain of salt. With a grain of salt. Larger variance means the data are more spread out. Larger variance. And also standard deviation, but we're talking about variance now. So largest variance means data are less certain, more spread out around the mean. And I can really write the same statement. Larger variance means data are more spread out around the mean, and just flip the variance for a standard deviation, and this statement will still hold true. And the standard deviation has some intuitive meaning, average distance the data are away from the mean. The variance does not have nearly as intuitive meaning. Okay. By the way, if I was going to plot the standard deviation, it's kind of hard to plot. It's an average distance. So I'm going to need the mode now. So I'm going to use the green marker to sort of plot the standard deviation. So we have to be around the mean. I don't know, it would be something like, this. I have to somehow portray an average distance, right? Average distance of data to the mean. So more spread out variable, more spread out distribution, less certain, larger S. The variance doesn't work, right? We just square it. So it's the squared average distance. Doesn't work nearly as well. Okay, moving right along. The next few are pretty exotic. That doesn't mean they're never used. It means that when you use them, it is very unlikely that they're going to be reported as part of that table 1. So in class, we saw an article where table 1, the characteristics of your sample, is usually the first table that is presented. It is very unlikely that the next few numerical measures are going to make it into a table 1. But they're sometimes reported in figures. They're sometimes reported as a part of the supplement. And sometimes we do look at them. And by the way, this guy right here, skewness, I've already referenced it using different set of words. And kurtosis is another thing that I've referenced using a very different set of words. And now we're just going to put a number to my many, many words describing the shape of this distribution. But right now we're in this bullet point, trimmed mean, coefficient of variation. So trimmed mean. Because it is well known that the mean is affected by outliers, then people say, well, if that's the case, I'm going to compute my mean without considering the outliers. So we say trim arbitrarily, that's the key, X% from top and bottom of the distribution. So by trim, we can say remove arbitrarily some percentage from the top and the bottom of our distribution. So the interquartile range is the middle 50%. If I wanted to remove, say, the top 5% and the bottom 5%, I would be left with the middle 90% of a distribution. If I wanted to trim the top 10% and the bottom 10%, I would be left with the middle 80% of the distribution. And usually this number, is something around 5% or 10%. So then you are computing the average, just a regular average, using the trimmed data. So the middle, 100 minus X% of the data. I'm not going to get too far into the notation. Using just the middle observations. And that's why this is called the trimmed mean. What the key word is here, this makes a lot of intuitive sense. If you think about it, that's how, for example, the Olympics are scored. Oftentimes they remove from the average the top judge and the bottom judge. But still, for science, the fact that we just pick an arbitrary percent of data to simply remove from consideration, that makes me itchy. That's why I personally have not used the trim mean hardly ever. The other, I think, thing that makes me itchy is when you collect data with your blood, sweat, and tears, you collect every observation. You don't know prior to making a plot like this which of the data are going to be outliers. You're going to be the amount of effort to collect data, 100% of your data, is the same whether it's an outlier or the median, around the median, right? The trim mean specifically removes data that was, very difficult to collect, possibly, from consideration, and it kind of calls certain data points invalid. It calls it invalid to inform the middle of the distribution. Maybe. That's why it is a real numerical measure, but one that, again, I'm not saying don't ever use it. I'm saying maybe if you were gonna use it, change how much you trim. Maybe you just trim the top 1% and the bottom 1%. Then it's almost the average. It's using 98% of your data, using the middle 98% of the data. Maybe you could even trim 0.5%. But still, if I'm reviewing a paper, that's a very arbitrary decision that a researcher makes. And so I would be curious as to why someone made that decision. Maybe you have a pet hypothesis in mind, And the average, when you use the good old average, your hypothesis becomes whatever untrue. When you use the trimmed average at a certain setting here, it becomes true. And that's just not great science. Let me know in class if you think trimmed means are really useful in your field. Do let me know. You are encouraged to disagree with me. But I'm just presenting how data are sort of interacting with these numerical measures, these tools to summarize n pieces of information into a single number. And sometimes that distillation process is useful. Sometimes it is less useful. Sometimes it is more useful. Sometimes it is completely invalid. The trimmed mean is not an invalid measure, but it is one that requires an arbitrary specification, and it requires you to just completely disregard some of your data. So use it carefully. All right. The next one that I see pop up sometimes, I did say these were rare, is coefficient of variation. Similar to the trimmed mean, please let me know if the coefficient of variation is something that you care deeply about, because then next time I teach this class, I will say something about that. Coefficient of variation. It's usually, I've seen C or CV as the notation, and it's just S over X bar, right? The sample standard deviation divided by this is just division, divided by the sample mean. You're finding how you're sort of evaluating the magnitude of the standard deviation relative to the average. That's, it sort of feels to me like it's the weather. It's another measure of spread in your data. If this coefficient of variation is high, then your standard deviation is large relative to your average. If this coefficient of variation is small, then your standard deviation is small relative to your average. It is a measure of spread. Also, by the way, affected by outliers, right? Because both the numerator and the denominator are affected by outliers. And you tend to square the sucker in the numerator. So just be careful. Be careful how you use this. Just wanted to make sure I mention it, just in case it's something that is widely used in your guys' field. All right. The next few, I've mentioned that I've already described them using English language words, but now these two measures get a number. We take our data set and we distill it to a single number. Skewness and kurtosis. Skewness and kurtosis. Skewness, I don't know what the standard notation is for skewness. It's a measure of the shape it can be left skewed. It can be right skewed. Or it can be symmetric. Or in other words, not skewed. Left skewed, we say that the left hand tail is longer. And for a left skewed data set, we have skewness less than 0, negative skewness. For a right skewed data set, the right hand tail is longer and skewness is positive. this is my data set. This is an example of what a variable would look like if we had positive skewness in the sample. The reason I started with this is because out of these three options, left skewed, right skewed, or symmetric, at least in medical statistics, in my experience, there's a lot of things that are either symmetric or right skewed. I have not personally seen a lot of variables that are left skewed. Again, let me know if that's not the case. I would love to hear an example of where there's an important left skewed variable out there. But most of the time, that right-hand tail is longer than the left-hand tail. That's because we're dealing with a lot of things like counts, where you're bounded below by 0, and so there is not much room for that left-hand tail to go. Remember, what we're discussing applies, roughly speaking, to both continuous and discrete. And a very popular kind of quantitative discrete variable is a count, where this low would be just a 0. So there's just nowhere for that left-hand tail to go. And so data are either symmetric or right skewed. And again, this is a qualitative description on the right. There is a number, which is the skewness. If that number is negative, then it's a left skewed variable. If that number is positive, it is a right skewed variable. If the number is 0, then it is, left-hand tail is about the same, approximately the same as right-hand tail. We say that our distribution is symmetric. It is not skewed. The skewness is 0. And this happens a lot when our data are not bounded. So in class, we had a lot of examples of various like liver score, where the numbers go between 9 and 40. It is possible that when you collect data, your data can be towards the middle of that range. And so then your distribution is not going to be bouncing up against those bounds. Then you might, depending on your sample, you might have an unskewed symmetric data set. Or again, just picking a liver score, because that's what I'm remembering, if you're collecting a sample with low liver scores, they can't be below 9. And so you will then have a right skewed data set. Other way around, if you're collecting data and you have mostly high liver scores, they can't be above 40. So that will introduce most likely a longer left-hand tail, and therefore a left skewed variable with negative skewness, skewed towards the longer tail. Okay, kurtosis. So these become a little bit more difficult to describe. Kurtosis is also a number. You can take a variable, quantitative variable, and distill, similar to skewness, we can distill kurtosis down to a single number. Kurtosis so sometimes it'll be called a measure of how peaky a distribution is. Measure of tendency towards the extremes. So these are the opposites, what I just wrote. If a distribution is peaky, then we have most of the data around the average, and the kurtosis is low. So high peakiness, a peaky distribution means data have small tails. Low kurtosis. You can also think of the opposite, how much data falls into the tails. So it can be measure of how thick the tails are. You can think of this as tendency to the extremes, almost like the anti-average. Thick tails, well, data have extremes, high kurtosis. But a fair question with kurtosis and skewness, how high is a really thick-tailed example? So it is very, very difficult. The units of skewness and kurtosis are largely uninterpretable. So they're very much descriptive. They're very much hypothesis generating. You get a right-skewed variable, that's tendency towards a large positive values. You can have a symmetric distribution that is still have a high kurtosis if the tails are relatively thick. These are numerical summaries. They tend to be hypothesis generating, as I mentioned, less so hypothesis sort of confirming. All right. Moving right along into a different set of variables to close out this video. I mentioned at the beginning that categorical data tend to be difficult to analyze, but tend to be relatively simple to plot. When it comes to categorical ordered and categorical unordered data, what you're recording, the numerical summaries, are relative frequencies. Right, so what you're recording is number of observations in a specific category out of n, which is our sample size. And that is true for both ordered and unordered data. The only thing that changes, of course, is whether these categories can be meaningfully ordered between ordered and unordered or nominal data. And then, you are basically plotting these relative frequencies. And you can multiply by 100% to get percentages if you'd like. All right, so that it almost will look like a histogram, but you have to be careful with the, let's call this an ordered categorical variable. These bins have to be the categories, right? If my ordered categorical variable is, for example, cancer stages, stage 1, 2, 3, 4. Then these, bins are different from the bins of a quantitative histogram because they can't be arbitrary, right? They have to be, all right, here is the bin for stage 1, and then here is the bin for stage 2. Here is the bin for stage 3. And then here is the bin for stage 4. And we know stage 4 is worse than stage 1. That's what makes it an ordered categorical variable. This is usually a relative frequency. So this is going to be between 0 and 1. And maybe I'm pulling data from SEER, for example, maybe, for example, from a SEER database. Which stands for Surveillance, Epidemiology, and End Results Program of the United States. It's a series of data collected in cancer registries from all over the country. I think they've recently increased the number of registries to 21. New states include states like Wisconsin, if I'm not mistaken, and New Jersey, I believe. But we're getting our distribution of stages for a particular cancer. Let's call it cancer stages, lung cancer. Lung cancer, the biggest killer of men, for sure. I think the second most common cause of cancer deaths for women, only behind breast cancer. And so, what this might look like is, suppose maybe about 25% of the sample is stage 1, maybe a little bit more is stage 2, maybe the most common is stage 3, but then of course, okay, this is approximately maybe 0.2, 0.2, 0.5, the way I drew this. If this is 20% are in stage 1, 20% are in stage 2, and 50% are in stage 3. Notice that the height of this next bar can't be 75%. Right? This doesn't make sense because if 20% are in stage 1, 20% are in stage 2, 50% are in stage 3, then we only have 10% left. So the height of this bar has to reflect that we are taking the same categorical variable, we're just graphing its relative frequencies. So there, let's make that average to 20%. There we go. Then this has to be like 10%. 40 plus 50 is 90, plus 10% is 100%. So this would be a valid tool to depict distribution of stages for something like lung cancer in your sample. So these relative frequencies add up to 1 or 100%, depending on whether you got percentages here or not. And I would say nothing changes really for unordered data, right? Whether it's, how many people are enrolled in the clinical research program versus MPH. There's no real good way to order those two, but the actual graphic doesn't change much for ordered versus unordered data. Sometimes you will see these as maybe stacked, but I am not going to get that sophisticated with sort of pencil and paper tools. If we work with a stacked bar graph, we'll let software design that for us. One thing to note, concepts around caution. Concepts around the mean, the standard deviation, really have to be applied very carefully. Because, measure of spread, okay, so what are the units of the measure of spread? If I was measuring PSA levels, PSA is a concentration of a certain protein per milliliter, I believe, or nanoliter of blood. So the average is going to have units, milligrams per nanoliter of blood. the standard deviation will also have those units. But if my categories are stages of cancer, is the standard deviation going to be a stage of cancer? Well, we can't invent a 1.5 stage of cancer. We also can't invent the 5th stage. So, we can't just take the standard deviation from the quantitative world and apply it into the categorical world. To be clear, there are measures of spread for categorical data. It's just not the numeric standard deviation, square root of a sum of how every data point, distance of every data point to the average squared over n minus 1. The average too, we can take something like the weighted average. The weighted average might be okay. Stages 1 through 4, at least it's ordered. So you can maybe get away with like an average stage by weighting using these frequencies as weights. So my weighted stage will be mostly an average of these 3, but it becomes more and more sort of finicky. You can pick the mode if you really want to. Right? The mode still applies. It is the most common level of my variable. It's just sort of not called that when there are only 4 possible levels, but the mode very much still applies. The median might also apply, right? The median is just the middle data. Median is also okay because it is just the stage that leaves 50% of the data below itself and 50% of the data above itself. It's the median stage. Probably the median stage would be either stage 2 or stage 3. Well, might be depending on what this exact number is. Most likely it would be stage 3, the way I drew this. That's 50% fall into this stage 3 exactly. So the next observation on the cusp might be the median. But the average, the standard deviation, skewness and kurtosis. Have to be really careful, right? Skewness is the shape of the distribution, but why couldn't we have multiple modes? Why couldn't we have something that looks like this? By the way, multimodal is very much a way to describe a data set. And I'm sort of dragging this lesson on, but I want to make this last point. That skewness and kurtosis, I think, makes very little sense when it comes to categorical data. Skewness can, in the case I just described, where there's a single prominent category, but why couldn't we look like this? We have maybe, 25% here, 25% here. And then 50% split between these two, I hate making up data, by the way. Here, we'll do it this way. Like, is this a symmetric distribution? I don't know. These concepts just don't have the same meaning. They don't really describe the shape when we're dealing with categorical data. Okay. I think it's time to end this lesson. We've described graphical and numerical summaries. On Thursday, we're going to look at some articles and we're going to practice summarizing our data sets using all these tools. So I will see you guys on Thursday.